Pretty
good.
Pretty good. Are there questions at all before we get started?
I actually had one on the goodness of fit test.
Okay.
Could you clarify again what our null and alternative hypotheses are for that when we do the goodness of fit?
So when you're doing the goodness of fit, is that the null hypothesis is that the distribution is what you say it is,
Oh, okay.
and then the alternative hypothesis is that it's not.
Okay. Thank you.
Oh, you're welcome. Anything else at all? All right, so I couldn't remember this morning if I had asked you to watch the video that I posted on contingency tables or not. So to see whether or not I just want to go through the construction just real quick. I'll let you go watch the video. I don't want to spend the whole reason I do the video is so I don't spend class time on it. But the idea behind the contingency tables, let me see if I can get to the actual formula here. All right. So you've got a population that can be divided up in a couple of different ways. So you've got class. I just wrote them as groups and categories according to what the example problem that I gave in the video. But you can slice it up into pieces this way, or pieces this way. So then you've got observations that are in each of these categories for each of these groups. So we're denoting these with the y sub ij's. And then you've got a total number of observations in each of the groups. So certainly, if we know the probability that of a particular observation falls into a group, then we can calculate the expected value just by taking the number that are in that group and multiplying it by the probability. So that's all this n sub j, p sub ij is talking about. So when we're doing these contingency tables, the idea here is that however these things are distributed in a particular category for one group, they should be distributed in a similar fashion across the rest of the groups. So that was why I used the example to start off the video of, do faculty at different institutions split their time up into teaching, research, and service in similar ways? So that if somebody spends 50% of their time on teaching at one school, that should mean that they spend 50% of their time on teaching at any other school. So that was the motivation example that I tried to give at the beginning of the video. All right, so these would be your expected values. So if I go across a particular group, I know that if I take, just from the same reasoning that we did with the goodness of fit tests, if you do your observed minus your expected and square it, and then divide by your expected and add all of those up, you should get something that's, if these really do represent your probabilities correctly, then you should get something that's approximately chi-squared. And again, on k minus 1 degrees of freedom, because you lose a degree of freedom, don't really lose a degree of freedom. There's not a degree of freedom for the last one, because once the other ones are completely apportioned, the last one's completely determined. So you don't have a degree of freedom there. This looks exactly like what we did in the previous section with the goodness of fit. It's the same idea. It's the same kind of statistic. All right, so then if we sum up all of these over all of the groups, we get something that's approximately h times k minus 1. Because I'm just summing up, we think about these all being independent, so I'm summing up independent random variables that are approximately chi-squared. So if I add up h of them, I should get h times that many degrees of freedom, because we know we add the degrees of freedom in that case. Now, of course, we don't typically have these p's given to us, so we have to approximate them. So the idea behind the approximation is that you just go across a group and divide it by the total. So what I mean is here, if I go back, If I sum up across a group, that gives me the total that's in that group, of course. But then if I divide that by the total, that tells me the percent of the population that should be in that particular group. I think I added the, I should add down the group, sorry, this way. If I get down here to the bottom, that should tell me the percentage of the whole population that's in a particular category. I said that backwards. When you add up across this column, you get the percent of the population that's in that particular category. So we're going to estimate these P sub ij's by doing the percentage, if you will, of the entire population that's in a particular category. So that's like if Millikan faculty spend 50% of their time on teaching, then all faculty across all institutions should be spending 50% of their time on teaching if they're distributed in similar fashions. So that's why we're summing across or down the column in a particular category and dividing it by the number of total number that's in the population. So we have to make estimates here, but we only really need to estimate k-1 probabilities, because if we know the k-1 probabilities, we know the last one. So we're making k-1 estimates, and again, remember that when we make those estimates, that we have to subtract that off from our degrees of freedom, and I really should have parentheses around that k-1. So you end up with something that's approximately a chi-squared on h-1 times k-1 degrees of freedom. And so this is going to be our test statistic that we're going to check against a chi-squared distribution. So to that end, let's spend some time on doing that in Excel. So this is just the very, very first problem in section 2 of chapter 8. So they've got, they want to see if nurses distribute their time across 6 different categories, and they want to know if the 2 different groups of nurses are spending their time in those categories in roughly the same ways. So maybe it's a day shift nurse and a night shift nurse, if you will. All right, so how do we use Excel to help us? Well, remember that we've got all these things that we have to compute. So to start with, the first thing I'm going to do is add up the rows and the columns. So I'm going to do the sum across the rows because I need that value. And then I'll copy it down. And I also need the sum across the down the columns. So I'll do that one. And I will copy that across. I also need the total, because remember, from the total we have to use that as our denominator to get our percentages in the categories. So I can either drag this one down or this one across, either way, and I'll still get my total in that lower right hand corner. So this is your overall total. And then if these are your categories 1 through 6. So assuming that we are distributing by group in an appropriate manner, if it's a similar distribution across the groups for the different categories, then the percentages that I will use to be able to calculate our expected values are going to be 148 over 500. That percentage of the time they spend on category 1. I would do 62 over 500. That percentage of the time they spend in category 2, and so on across. When we have those percentages then for the different categories, to figure out the expected value in each group across those categories, I'll take those percentages and multiply it by the total that are in that group. So this table up here is our observation table. We're going to do our expected table now. So I still have categories 1 through 6. And I have groups 1 and 2. To get your expected number that I need to, for this cell here, I need to multiply the percentage of the time, which is the 148 here, and divided by the total here. Now I have to be careful because I want to be able to copy this across. I don't want to have to type this in every single time. When I copy across, I want the column to change here without any issue, but I'm not going to want the row to change. What I mean is that if I want to copy this cell down to the next row, if I just copy this without making something an absolute cell reference, it's going to try to go down here to the next row. It'll go to the row 5 and it'll give you 0 because there's nothing there. So to make that what I want the column to change. As I go across, I want the columns to change, but I don't want the row to change. Well, if I hit F4, that makes an absolute on both of them. If I hit it again, it starts to cycle around. So that one fixes the row. If I have it like B $4, it fixes the row but not the column. So if I take this cell now and copy it across, it'll change the column, but when I copy it down, it won't change the row, which is exactly what I want. All right, so this is, again, representing the percentage of the time a group should be spending in category 1, assuming that percentages are split up across categories equally for the different groups. Okay? I need to get expected value. Remember, to get expected value, I need to take this product times the total in that particular group. Now, again, I want to try to copy this down. Now, when I go across, I don't want to change the column, because if I change the column, I start referencing these other ones that have zeros in them. So I don't want to change the column, but when I copy it down, I do want to change the row. So let me, again, hit F4. That puts absolute references on both the column and the row. I hit it again. It's just on the row, but that's not what I want. I want the other. I want it just on the column. So I hit F4 3 times to get the absolute cell reference on the column and not the row. By the way, you can always just type the $ incorrectly, or indirectly, I mean. You don't have to use the F4 button if you just want to type it in. All right. So again, just to go over this fraction is representing the percent of the time that that you should be in category 1 in this particular case, and we're multiplying it by the total that's in group 1 to get an expected number of observations in group 1 category 1. But now that I've done that, I can now copy this across, and I know what I forgot to do. Darn it. Guess what I forgot to do? I also don't want the H4 to change at all. I need absolute cell references on that whole thing. Sorry about that. And then I copy this across and copy it down. And these are now our expected numbers. If we add these up, if you have your sums in here, they should add up to the same, the overall total should be the same. You should still have 300 here, you still should have 500 here, and you should have all of these overall totals the same. If you do the sum here, down this column, you should get the same as the sum in the first column, because all we're doing is just splitting it up by expected value. So again, notice all of those are the same. You don't have to do these what I'm doing right now, by the way. I'm just showing you that they should be exactly the same as the totals were in your previous table with the observeds. Okay, it's the only reason why I did it. You don't have to put these in here at all. But if you've done your entries correctly in your expected tables, you should get the same numbers. That's all I'm saying. All right, so now we calculate the statistic in the exact same way. So I'm just going to make an entire table with observed minus expected squared divided by expected. So I'll still put the labels in there. The labels, unlike ANOVA, the labels here are not important. I just put it for my own personal use to be able to see these things. All right, so this is going to be observed, which is up there in B2, minus expected, which is down here in B8, squared, and then divide it by B8. I don't need to put any absolute cell references on this because I'm going to copy across and down exactly like I want to. So I don't have to worry about any absolute cell references here. Highlight it, pull it across, and pull it down. Those are our observed minus our expecteds. So now for our test statistic, all we're going to do is add up all of these. And that gives us our test statistic, in this case, a 3.23. And then we compare it to a chi-squared distribution, just like we did in the previous section when we did goodness of fit. So if we want to compare it to a critical value, we'll do our chi-square inverse, and we're always going to be on the greater sign of things. All of these are one-tailed tests. So we'll do the right tail. The probability is 0.05. Now I need degrees of freedom. Remember that according to how we develop this, your degrees of freedom are number of groups minus 1 times number of categories minus 1. There's 2 groups and 6 categories, so our degrees of freedom here will be 5. So we'll compare our test statistic to that critical value. So in this case, we do not reject. So it seems like the nurses, depending on groups, are spending their times in equal or relatively equal percentages. That there's not a statistically significant difference in the ways that the nurses are distributing their times across categories depending on what group. So again, maybe a little bit more context. The night shift nurses are spending their time in similar ways as the day shift nurses are. All right, if you wanted a p-value for this particular test, you would do the same idea that we did before. So you would do your chi-squared distribution. The test stat is up here, the 3.23-ish. And again, the degrees of freedom was 5. And we get 0.66. So again, certainly did not reject, and with that p-value that high, there's absolutely no evidence at all that we could make any type of statistical conclusion to say that they're not spending their time in different ways, that they're spending their time in the same way. Any questions on how that stuff was set up at all? Were you okay with that? I'm just making sure my speaker is not shut off like it was last time.
Yeah, I'm good.
You good? Okay. I went and actually checked my speaker that time because last time I remember that people were raising their hands and putting things in the chat. So just wanted to make sure. Oops, somebody did something. It went away too fast. What happened? Did somebody raise their hand?
I'll put a thumbs up.
Oh, thank you. I just, when the little notification came up on the screen, I hit the screen so fast it went away almost instantaneously. So thanks for the thumbs up, though. I appreciate it. All right, let's do another one. Make sure we have the idea here. So this is actually a combination of problems 3 and problem 4. Problem 3 just had the 2 classes to start with, and the problem 4 had said add a third class and see what happens. All right, so they've got 3 classes of 15 students. They had different methods of instruction, and they were given scores on a standardized test. So in this case, it wants to know if the distributions were of the scores by low, middle, and high were relatively the same. So let's see how we might come up with the combined sample into 3 equal parts of low, middle, and high. So if we combine the sample, let's just do that to start with. So take all of these values, just put it down below it, I guess. I need to organize this data in some fashion. So what I will do is put it all in one column so that I can organize it. Because it says it asks us to divide it into low, middle, and high. However we want to do that. All right, so bear with me here. We'll get there eventually. Probably. And then we had 44 and 78 and 69. All right, so let me highlight this data. And sort it. So go over here, sum, sort, smallest to largest. All right. So now that I have the data sorted, it asks us to combine the sample, go in 3 equal parts where we have a low part, so the lowest 15, right? There's 45 total, it looks like here. Lowest 15, middle 15, highest 15. So the low would start here, and then if we go down 15, that would be down to row, what, 23 would give me to 15, I believe. So this should be your middle, and then go down to your next 15. So if I go 24 to 40, or 38, should get me to 15. So this should be your high. And this should go down to 53. Yeah. All right. So that gives us 15 values in each of these. The only reason why I sorted it, there's probably an Excel command that I could have done this easier, but I don't remember what it is off the top. I believe there is an Excel command that I could have done this easier, but I don't remember what it is off the top of my head. So this was the easiest way to do it for me. All right. So what do we need to count? We want to know for each of the classes, for class U, class V, and class W, we want to know how many fall into the low value, how many fall into the middle value, and how many fall into the high value. So we've got 3 classes again. So we've got class U, and we've got class V, and we've got class W. And we're going to divide this up into 3 categories of low, middle, and high. And we're going to count the number of observations in each class that are in these ranges. So I want for class U, I want to be, for low, I want to be between 39 and 61. So we'll do that countifs command again. So here is class U. I want to use the same criteria going down the column, so I will make an absolute cell reference here. I don't want to change. I don't know if I need to do that or not, now that I'm thinking about it. No, let's just not do it that way. I'll just re-highlight it now that I'm thinking about it. I don't want to mess it up and then have to redo it anyway. All right. So in that particular range, we want this to be, I don't need to worry about the low because nothing was lower than 39 anyway. So I'm just going to say less than less than or equal to, I'm going to go ahead and type in the equal to part, less than or equal to 61, because that was the high end of the low values. Now I'm going to copy this just so I don't have to retype all of it in again. So here, I don't want this one, I want this range. And then in here, I don't want this, I want this range for W. So it's the same command for all of them. I just need to plug in the different criteria, the ranges where we had those values.
Would that have worked anyway if you just drug it down because you're using relative cell references?
Well, the thing is, I think, I'll just try it because I can always hit undo, right? Yeah, so unfortunately, that was my issue. I didn't think it would. It would have, had this data not been in 2 rows. The reason what's causing the problem is when I pull this down, it only does the relative cell reference by 1 row, and it really needs to jump by 2.
Oh, okay.
That's why. So if I would have not typed it in like the book had it there and just typed it in across the entire row, then yeah, it would have been just fine.
Were we allowed to type it into one entire row?
Oh, absolutely. Yeah, you can type it in however you want. I don't care. I just typed it in there and it fit the way the data was in the book. Actually, as long as you're doing the computations correctly, I couldn't care less how you type it in.
Okay, thank you, Doctor.
Yep. All right. So now this one I need to be between 62 and... Yes, Sam?
Dr. Joe, could you leave that screen right there so I can see the command?
Sure.
So you don't fix the row at all? You leave it as is, E2 colon I3?
I did because I changed it for each one.
Oh.
I wasn't actually copying that command. And the reason, again, why is because if I just try to copy it down one row, it's not going to work because the data jumps 2 rows to the next group. And the relative cell reference will only change it by 1.
Okay. Does the less than or equal to have to be in quotes?
Yes.
Okay.
Yeah, because you're basically what you're telling Excel is that it's a string that you want it to understand that it's a string, and it has to know what that string is. That's what the quotes are for. So it has to read it as a string so it understands what the symbols are, rather than a number.
How come you're doing for the middle? Shouldn't it be, how do you do between 2 values then?
I was just going to do that right now. So this one I need to be in between the 2 values. I don't remember what the bottom value is here for the high value is for middle. It's 78 is the last one in the middle range. All right, so I need this greater than or equal to 62 because that was the lowest in the middle range. And then same range of cells, the B2 through I3. So I just copied and pasted the text, but you could have gone up and just grabbed it from the cells above again. And then I want that less than or equal to 78. And then again, I'm going to copy this command so that I don't have to re-enter it again in the next cells. So I need to change the B2 and I3 to the one for V and the one for V. So all I did was just highlight the B2 to I3 and just replaced it again. And then I'm going to do the same thing for the W. I'm going to highlight the B2 to I3 and replace those. Ooh, hey, that's fun. What did that do? That was weird. Don't do that. Anybody else talk to the computer like I do? All right.
No.
No? Oh, thanks. Good. I'm glad I'm the weird one. It's fine.
I don't even know what you asked.
Oh, I said, does anybody else talk to the computer like I do?
Yeah, sometimes. I want it to work.
Yeah. I tend to swear at it when it's not doing what I want it to do. All right.
It'd be like that.
Say that again.
It'd be like that sometimes.
Yeah. And then the last one we want to do greater than or equal to 79. So in here again, delete all this stuff off, and I just want the 79 here for greater than or equal to. And if I copy that, and then change the range again. And then change the range again. Whew, that was a lot of work to get to that point. All right, there's our observed. So just to make sure I label this correctly, this is the observed values. The rest of this should be fairly straightforward. Again, to get our expecteds, we need the different sums. So this will be the sum across our row for the 3 rows. This will be the sum across or down the columns for the 3 columns. Now, it should make sense that these are all 15. I'm just going through the process. The reason why these are all 15, again, is because they gave us 3 classes with 15 students. So this should be 15 across each row. And we divided it into 3 equal classes of low, middle, high. So when we go down the columns, this should also be 15. So that's not a huge surprise. And then again, for the total here, it's 45. So in this one, you could have just used the 15 and the 45. But I wanted to show you how to go through this generally, because generally you're not going to have equal-sized groups and equal-sized categories. So then again, let's do our expecteds. So we have low, middle, high, and group 1, group 2, group 3. We use column, but I don't want to change the row, divided by total, and I don't want that one to change at all. That's the percentage that should be in the first category, and then we multiply it by the total that's in the first group, and I don't want the column to change on that one. So that gives us our expected number in that particular category, and then I'm just going to copy across and down, and not a huge surprise that it should be 5, right? We used equal-sized groups with equal chances of being in a particular category. So all of these expected values all should be 5. That just makes sense from what we've done, how we set this problem up. So if I do observed minus expected divided by expected, I don't really need the category labels here. If you don't want to copy the category labels down each time, that's fine. I don't care. Low, okay, so observed minus expected squared divided by expected. And copy everywhere. And then when we calculate our test statistic, we just need to add all of those up. So we get a test statistic of 10.4, and our critical value is, using our chi-squared, we're doing the alpha is 0.05, and then degrees of freedom here, again, we have 3 groups and 3 categories. So we subtract off 1 from each of those and then multiply. So we have 2 times 2 gives us 4 for our degrees of freedom. So in this case, we do reject H0. So what that means is that, for this purpose, is that the distribution across the different categories, low, middle, and high, differ as you go by class, which you can kind of see here. In this column in particular, it looks like there's a nice big difference, right? Class U didn't do so hot on the exam. Class W did pretty well on the exam. So you can kind of see that there is a difference in the distribution across the different categories based on the class. And then again, if you're asked to find the p-value, you would do your chi-squared. Actually, this is an approximate p-value because it's an approximate chi-squared distribution. And then we do the chi-squared distribution on your test statistic for 4 degrees of freedom here and get 0.03.
Which class are we?
Which class are you? Do you really want to know?
Yes.
I don't know. I think you're all on the high end. I have all high opinions of all of you.
So sweet.
Oh, I know. I try to be. Questions on this one? All right.
So what's our interpretation?
The interpretation here is that there's a difference in how the class is performed in this particular interpretation. I mean, that literally just from the end of the test that's the only conclusion that we can really make, is that there is a difference in performance based on class.
We can't say anything about the distribution or anything, just that they perform different.
Correct. That's all we can say from this particular test, that there really is a difference, and then you would want to do other types of tests to see if there really was a difference. For example, if you wanted to see that class W had the best average, then you could do a hypothesis test 2 at a time by the means kind of thing. You could do it that way. You just have to do more testing, which is not unheard of. You do one test to see if there's things that you would throw out, and then go from there and see if there's another test to do. This is not unheard of in statistical testing. All right. So in this same section, we can do a similar concept when we're looking for independence of variables. So let me go over here and pull up another presentation. All right, so let's say we want to see if two different ideas are independent of each other. So let's say we have a random variable that can be partitioned into k different events, and a second random variable that can be partitioned into h different events. So we're going to use the a's to represent the events for variable 1 and the b's to represent variable 2 here. So let's let our y sub ij be the number of observations in the intersection of the two things. So y sub ij is looking at when a sub I and b sub j happen at the same time. And certainly there are k times h such events that can happen that way. All right, so if we have the probability that the probability of the event a sub I intersect b sub j, we're going to denote that with a p sub ij, then we can do the exact same thing that we've done in the last two topics that we've talked about. This n, if n is the overall number of observations that you're making, so it's it would be the total that's in all of the A's and all of the B's. It's the partition, so it's the total number of observations that are made, and multiply it by the probability that you're in that particular event. That would be your expected number that you should see of those observations. If you do all of this, again, here there are k times h such events, but the last one, the very, very last one, will be completely determined because we've partitioned things up, right? Everything's been partitioned, so if you figure out the first kh minus 1, then you don't have anything to determine for the last one. So you get something that's approximately chi squared on kh minus 1 degrees of freedom. Okay? Notice this looks a heck of a lot like the setup that we've been doing. All right. Our test here is going to be whether or not the different events are independent of each other. So that's what we're going to be testing. So when we do that, that means that we really, remember for independence, the probability of an intersection is the product of the probabilities of each event. That's what gives us independence. So our null hypothesis is that all of the events here that we have, the A's and the B's, are independent of each other. And so our alternative hypothesis will be that at least one pair are not independent. All right, so to figure out the probabilities of the different ones, we're going to let, and then this lovely notation again with the dot notation, p sub I dot is going to be the probability of a particular a sub I. So to get a probability of a particular a sub I, that means that we're going to add across our h's, or all of the, sorry, from the 1 to h, we're going to add across our second subscript here. So we're going to go across all of the x2s and leave the I fixed. So we're going to go across all the x2s to get the probability of a sub I. We can add up the probabilities to get this probability of this event because, again, we have partitions, right? The b is partitioned up a particular a sub I. So if I add across of all the b's, I'll get the totality that should be in the a sub I. And then the p dot j here similar fashion, we're going to add up down across all the x1s, or the a's, I should say, to get the b sub j. And the reason I put this parenthetical here to say that remember that they're mutually exclusive is the fact that we're just adding probabilities together to get the total probability. That's what we mean by the partition. Then we can rephrase our null hypothesis in this fashion, that our p sub ij should be p sub I dot times p sub dot j. All right, so how are we going to get estimates for these things? Well, if I want an estimate for pi dot, and again, is our total number of observations, I will sum all of the y sub ij's where I move my j across. That's going to give me an estimate for the p sub I dot. And then likewise for the p sub dot j. That's going to give me estimates for each of those. And then notice here, I've got to make h minus 1 estimates here. Once I know h minus 1 of them, I know the last one. So I have to make h minus 1 estimates here and k minus 1 estimates here. So the total number of estimates that we have for parameters is k plus h minus 2. So if I go back to the original statistic here, this test statistic that we're calculating is approximately chi-squared on the total minus the number of estimates we have to make, which looks like k minus 1 times h minus 1, which is exactly the same number of degrees of freedom we had in the previous example when we did the contingency tables. I know that was a lot of information. I wanted to get to this part because I want to show you a couple of examples using this independence idea and show you what the test statistic looks like and the degrees of freedom looks like. This test statistic looks similar to the one we just did for contingency tables, right? We've got observed minus expected over expected. We just have a slightly different computation here for our probabilities because we're trying to test for independence. So we want to know if the probabilities multiply together to give you the probability in the individual spot. So let's do that. Go bump over to Excel. And let's look at 8.5. All right, so in this case, it wants to know if gender and opinion on smoking in public places are independent of one another. So we've got the groups broken up into male and female. So that's one characteristic that we broke up our group into. And then we have favor, oppose, or no opinion. That's the other one. All right, so we're going to start this off in a similar fashion that we did in the previous problems. So we'll add up across the row here to get the total for males. And we will copy that down. And we will add up down the columns. And copy that across. I'm just going to pull it all the way across to get to the total number that we need. These are your observations, and we need these totals to help us get the different values that we need. All right. So let's talk about how we get our expected here. So I'll put the categories again so that we can see it. All right, so these were our number of observations that we had. We want expected now. Well, the total, of course, is the 1015 over here. So make that absolute cell reference. I don't want that to change. If I want a probability that we're in this particular category, well, I'm going to use, again, say you want the probability that you're in the favor category here. Well, then I'm going to total this up and divide by the total number of observations. So this probability is going to be given to us by the 564. I want to change the column but not the row, and then divide it by the total. And again, I don't want that to change at all. So this B4 divided by E4 is representing the probability that you're in the favor column. And then I need to multiply that by the 503 over here. Because I'm trying to test whether or not they're independent. So the probability of being in male is going to be estimated by the 503 over the 1015. So I'll take the 503, so E2, and then divide by the total again. Now, of course, notice that I've got n on top and a couple of n's on bottom, so one of those are going to cancel. This is a lot more than I actually need in here. And notice if you really, really are astute and paid attention to the previous stuff, notice I would have the exact same computation that we just did in the previous two problems, didn't we? We would have taken this value times that value over that value. So this is a lot more than I actually need to type in, because every single time you do these, a pair of n's are going to cancel. The reason I typed it in this way is so that you can actually see what we were talking about in the slide. This is total number of observations overall. This second piece right here is an estimation of the probability that you end up in the favor category. This piece right here is an estimation of that you end up in the male category. And if being male and favor are independent of one another, you should be able to multiply those two probabilities together to end up in the favor and male category. And then multiply them by the total gives you the expected number that should be in that category. Now again, like I just said, the way we're estimating these probabilities, an n is always going to cancel out on top and bottom. So what you have in a particular cell is going to look exactly like what we just did for contingency tables in the previous two examples. So you don't have to type in all this extra stuff. Actually, once you get one Excel sheet set up, you should be able to do all of the other ones in the exact same fashion. You may have to shrink your table or make your table bigger to fit the number of categories that you have in a particular problem, but the actual setup for the tables are exactly the same every single time. All right, so now we need to do observed minus expected squared over expected. So here's observed minus expected squared over expected. And copy. And copy. And then compute our test statistic in the exact same way that we've done in the previous two things that we've done. Add up all of these observations, add up all these computations of the observed minus the expected. There is your chi-squared, approximate chi-squared test statistic. We can figure out our critical value again by using the chi-squared distribution. Alpha 0.05. Degrees of freedom. We just said in the stuff that I went through on the slides, the degrees of freedom is the same as what we just did for contingency tables. It's number of categories here minus 1 times number of categories here minus 1. So we have 1 times 2, so we would have 2 degrees of freedom. So just barely, we do not reject. Just barely at that alpha level. If we wanted a p-value, see how close we were, we would use the chi-squared distribution right tail on our test statistic, and degrees of freedom was 2. So it's 0.0504. So really, really, really close. If your alpha were, say, 0.1 instead of 0.05, you would reject. So honestly, in this particular one, we would, on a technical basis, we would not reject H naught because of the fact that it's just a smidge smaller. But honestly, there is evidence here, at least at the 0.1 level and even at the 0.0504 level here, that male and gender and opinion on smoking in public places are not independent of one another. Any questions on that at all?
Did you just pick 0.05 just cuz, or?
Just because that's what we typically pick. But
Okay.
yeah. Usually what you really do is you look at the p-value and then you pick your alpha.
Would you, just based on the table, since the no opinion is so small, like there's just such a small number, would you want to pick a bigger alpha value or would you want to pick a smaller alpha value?
Actually, the no opinion's not what's throwing us off as much because those actually have small differences in their observed minus the expected. So I wouldn't worry about that, but the smallness of these numbers, unless it was causing these to be really, really skewed relative to the other ones, and that's not what's happening in this particular case. So I wouldn't worry about that at all relative to any type of conclusion as far as this one goes. To worry about them being small if it throws off your expected values more than what it should based on the size of the sample. Any other questions?
What was that other video you posted yesterday about these squares?
The least squares, that's for linear. That's not for this class. Did I add it to our class list? Because that means I put it in the wrong playlist. That one's for linear.
Was the